Hello, we're going to start section 7.3, electron configuration and quantum numbers. So by this time, according to Schrodinger's equations, the newest model of the atom had probability regions, not circular orbitals. So these shapes looked odder than you can probably imagine. They not only were they not just little orbital rings, they're shapes like spheres, dumbbells, clover leaves, and donuts. And then even beyond that, there's more lobed figures that I don't even know what they're called. So here's a few examples of the simpler looking ones. So you can see how the first one is sort of a spherical thing, and the density where it's more dense, you can tell that's has a greater likelihood that the electron would be there than out here, but it could be any of those places. It's just there's more higher probability where it's more dense. And see how it's kind of dumbbell shaped. So kind of like an hourglass type thing. And then there's even this little donut ring thing that goes around it. So this is just cut down the middle, looking at half of it. There are four numbers in a row that can be thought of as like the address for every single electron in every single atom. And each one of them is unique. No two electrons have the same quantum numbers. All four, they don't have all four of them. So we're going to talk about the first one first. So I've got them color coded. So the first one is the principal quantum number, and it's going to be the first one. It's pink. Then we've got the subshell or azimuthal quantum number, and I've got it yellow. The magnetic quantum number, and I've got it green. And then the spin or the magnetic momentum quantum number, and I have it blue. The first one, principal quantum number. Now, the letter that is its symbol is an N, which is obviously not the first letter, but there is an N in principal. So N simply refers to it's a whole number. The bigger the number is, the bigger size, the level where the energy level that contains the electron is, and the higher energy level it is. So they're all whole numbers. So 1, 2, 3, 4, etc. Now, also sometimes they're labeled letters starting with the letter K and then just proceeding from there. So K is the first level, L is the second level, M is the third level, and so on. Now, only so many electrons can fit in any certain energy level. As you go up on the energy levels, they get bigger, so they can hold more electrons. But the formula to know how many electrons maximum can fit in any level is whatever the principal quantum number N is, square that number and multiply it by 2. So the very first level, if N is 1, 1 squared would be 1 times 2. Only 2 electrons can fit in here. Okay. And then the second energy level, 2 squared would be 4 times 2 is 8. And then the third level can hold 18 and so on. So each time they can hold more electrons. So they're bigger, they're higher energy level, and they hold more electrons as they get bigger. Also, there are more sublevels that will fit in each energy level as you go up. So the first level only has one sublevel, and the next level, principal quantum number 2, has 2 possible sublevels, and it can hold a total of 8. Then the third principal quantum number can hold 3 sublevels, and the fourth one can hold 4, and so on. Now, they can, as we saw when we did our last lab where we did the metallic elements and did the flame test, those electrons were excited into a higher energy level, and then they released that energy and emitted light. So those kinds of energy levels are not their normal resting levels. So they're way out here. Okay. The second quantum number is the subshell or azimuthal quantum number, and its symbol is an L. So there are two L's in subshell or one in azimuthal. They these numbers you can find by subtracting one from n. So L is equal to whatever the energy level quantum number was minus one. This level narrows it down from the whole shell and tells which one of the sublevels or subshells it is. So if L is equal to 0, then it is an S subshell. If L is 1, then it's the P, or it's one of the P orbitals. And if it's 2, it has to be a D orbital or subshell. If it's 3, it has to be an F sublevel. Now, I told you they're weird looking. If it's 0, this is what the S sublevel looks like. This is the dumbbell shape. So there's one for the x-axis, and there's one for the y-axis, and there's one for the z-axis. And then angled around those are the D levels, and they're kind of clover leaf and donut and dumbbell shaped. And then these are just really weird lobed figures that are provided that fill in all the gaps that these others missed. The third quantum number is called the magnetic quantum number, and it is M sub L. And the possible choices for M sub L are the whatever L was, if it's 1, 2, 3, 4, or 0, your choices are negative L through all the way, including 0, all the way to positive L. So if L was 3, then it could be -3, -2, -1, 0, 1, 2, and +3. And if it's 0, then obviously the only choice it could be is 0. And if L was 1, then it could be -1, 0, or +1. So it just has a range of all the way from -L extending to +L. So this quantum number, the magnetic quantum number, it can describe which orientation it is in space with respect to the X, Y, and Z axis. So since there's no M in orientation, and there's no M in axes, and none of these are there's no M axis. So mag kind of sounds like max, sort of. So maxes, and it kind of rhymes maybe. So M for maxes or maxis, maybe. Anyway, these numbers tell which orientation the orbital was. So if L was 1, then we know it was one of the p orbitals. And if it's -1, so the choices for when L is 1 is -1, 0, and +1. So the x-axis, if it's the p orbital along the x-axis, it's -1. If it's the p orbital along the y-axis, it's 0. And if it's the p orbital along the z-axis, it is +1. So if L was 2, then it would be the D, those weird clover leaf ones, and I don't really understand exactly how they fit together. But there'd be 5 choices of different axes, and they fit around like the diagonals and things. But anyhow, these 3, when they overlap, they look like this. So sort of like a weather vane, you have like these 4 blades that swing around, and then it's this up and down axis as well. So kind of like a weather vane that might blow around in the wind. So this one's the -1, that one's 0, and that's +1. They're all different though. All those numbers describe a different orientation. So they range from -1 to +1 and include 0. Now, when all of those subshells, not just the P, when the S, the P, the D, the F, whatever places that atom has, all the electron orbitals, everything is covered. So um, whether it's just if it's a really tiny atom and it only has the s orbital, I mean, that's the only place the electrons will be. But if it's a larger atom, then it's going to have all these different areas, and all these places are covered by whatever orbitals that the size of that atom can have. So everything is mathematically described by one of these arrangements. No matter if we can't really figure out how these reconcile in our brains, how these shapes fit together and cover up everything, when they're all stacked on top of each other, the sum of all these electron clouds equals one giant spherical cloud with no gaps. Now, the last quantum number is the spin quantum number. And you'll like this one. It's the easiest one. It only has two choices. They can either spin from north to south, and we call that a +1/2, or an up spin. And the other way is -1/2 or a down spin. Now, the Pauli exclusion principle states that no two electrons in an atom may have the same set of four quantum numbers. At least one number has to be different because they're all unique. So it's kind of like they all have their own little mailbox. So here's an example of four quantum numbers. So n equals 3, L equals 1, M sub L equals -1, and M sub S equals -1/2. N tells us that it's the third energy level. The subshell quantum number L tells us that it's the p orbital. 1 is the p orbital. M sub L is the magnetic quantum number, and this tells us that it is the x-axis. -1 is the x-axis. And M sub S tells us that -1/2 tells us it has the down spin. Here's another one, n equals 2. The subshell quantum number is 1 again. M sub L is +1, and the spin quantum number is +1/2. So n equals 2 is the second energy level. The subshell quantum number 1 is the p orbital again. And then the magnetic quantum number is 1, which tells us it is the z-axis. And then the magnetic spin quantum number is +1/2, so it's got the up spin. Then here's a third set of quantum numbers. So n is the first energy level, and it only has one subshell. So 0 is equal to the s subshell. Then M sub L, or the magnetic quantum number, it can be -L, 0, or +L. Well, L was 0, so it can only be 0. And the s orbital doesn't have any axes. It's just one cloud. So there's no axis. And the spin quantum number is +1/2. So it's the up spin. So those are three examples. Now we'll talk about electron configurations. So electrons, there's a set of rules that scientists go by. Electrons fill energy levels in a very particular order, following 5 basic rules. So unless they tell us something else, we assume that the electrons and the protons are equal, and it's a neutral atom. The electrons occupy the lowest energy levels first, and then they file in and go from lowest to highest until everything is full with leaving no gaps. And then they end at the higher sublevel. There's a little bit of an exception when we get to the D, F, and higher orbitals, but we'll talk about that in a minute. According to Hund's rule, when we start filling up a P, a D, an F, or anything, any kind of sublevel that's larger than one orbital, if it holds more than 2 electrons. So if it holds 6, 10, 14, or whatever, we put 1 electron in each orbital before we start putting 2 electrons in any of the orbitals. So, when we did the spin quantum number, there's a up and a down electron. So we just put 1 electron in each one before we go back, and like the p orbitals, there's 3 of them. And we just put 1 electron in each one before we start going back and putting 2. Every orbital can only hold 2 electrons maximum. You can't put more than 2. And so this tells us how many electrons can fit in each sublevel. So S can hold 2, the P can hold 6, D can hold 10, and F can hold 14. This is probably not making sense yet, but it will in just a minute, so hold on. So this is an electron orbital diagram, and it has the first little bit of sublevels mapped out that we can put electrons in. Now, you might notice that some of these are out of order. So these are all in order until we get to 3, we get 3p, and then we go 4s, and then it's back to 3d and 4p. So if you write this list down, you'd think you'd go here and read it like a book and start at the left and go to the right, but that's not actually the way you do. They fill up in this order. So I've got these arrows in rainbow order to show they start with the red and go towards the purple. So I've got these sublevels written in that order. So even it starts out in order, but when it gets to 3p, the next one's 4s, and then 3d, so back to 3, and then 4p. That sounds really odd, but if you look up at the periodic chart, it's actually the way they're arranged, and there's a reason for that. So the 1s is hydrogen and helium. They're kind of separated by a big gulf, but they're both on the first level. Then the second energy level has the 2s over here, and then 2p, and then the 3s and the 3p, then the 4s, and then the 3d, and then the 4p. So the first and second groups are the s orbitals, and this whole chunk over here on the right from the green and the blue over here, well, the green is the p orbitals. This blue one is the other s orbital, part of the s orbital. And then all these down here are the d orbitals, and then these 2 rows down here are the f. And the reason I don't have any more letters written out here is because by the time we get to element number 118, it's in the 7p orbital, and we don't have any more to go to. So let's try doing an orbital diagram for carbon. It has 6 electrons, but so it has 6 electrons. So we are going to fill up each energy level, each box can hold no more than 2 electrons, and we're going to follow Hund's rule. And when we get to the p orbitals and the one or the d, the ones that can hold more than one orbital, we're going to do 1 in each box before we go back and put 2. So we have 6 electrons. Let's start with 1s. So we have an up and we have a down, and then we go to the second energy level, and we have an up and we have a down. So that's 4 electrons. Now we're going to do Hund's rule and put 1 in each box until we run out and use up our 6 electrons. So we have 4 so far, 5, 6, and then we stop. So that is the electron orbital diagram for carbon. So let's try another one that's, so these are the areas we have to pay attention for Hund's rule. So let's try another one that's got a lot more electrons, like 79, and that's down here in this D region, and it's after the F region. So this will give you a taste of how to get through and navigate all these odd placements on the periodic chart. We've already got 6 electrons. We've just got 73 to go now. So 7, 8, 9, 10, 11, 12, and then we put 1 in each thing. So 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So that's 36, so we don't forget it. Now we need more boxes. So 37, 38, and then this will be 5 up and 5 down. So 38 plus 10 is 48. And then this will be 3 up and 3 down, so 6 more. So 48 and 6 is 54. And then 2 more is 56. This is 7 boxes with 2 in each one will be 14 more. So that makes 70. And then this is 79. So we need to fill in 9 more arrows, 5 up and 4 down. So that gives us 79. So this is the electron orbital diagram for gold. And we filled up 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and then watch, we went down here because see this little red gap. So imagine a 3D, like cut this out and it sticks out projecting toward you, like a flap that sticks out and comes out of the page toward you. So this 4F row fits here projecting out to you, and this 5F row fits right there projecting out to you. So we did 6S and then 4F and then 5D and stopped here, right here for AU for gold. All right. Now, the last thing that we're going to talk about in this section are Lewis symbols. The electrons located in the S and the P sublevels of the highest energy level are referred to as valence electrons. For the valence electrons, there's a maximum of 8 electrons because you have 2 in the S and up to 6 in the P. So 2 plus 6 is 8. So no more than 8 for the valence electrons. These electrons are really important because they are typically the ones that are involved when we talk about chemical reactions. So Lewis symbols are handy visual representations showing each element with its valence electrons. It's just really easy to look at. It's going to be the element symbol for carbon. It's just a C. And since carbon has 4 valence electrons, so it has 6 total. So I did carbon because people, when they first start doing Lewis symbols, they want to put all 6 dots around carbon. But you have to remember, you look at what energy level it's in. So it's in this second period in the periodic chart. And the first 2 electrons would be in the 1s orbital. So the 2s orbital and the 2p orbitals are the only electrons that we're concerned with. So we ignore the first 2 electrons that are in carbon. We only talk about the 4 that are in the second energy level. Okay. So we have 1, 2, 3, 4. 4 electrons in the second energy level. So we draw a C and we put 1, 2, 3, 4. Now, fluorine is right here. It is number 9 on the chart, and it has 2 electrons in the 1s or sublevels, and it has 1, 2, 3, 4, 5, 6, 7 electrons in its valence electrons. So we're going to draw an F with 7 dots around it. So we have 2 on every side except for this side, so just 1 electron right here. So we kind of do like Hund's rule, and you just put 1 on each side, or you put 2 on each side. So if they have all 8, like neon is a noble gas, so it has its full valence. So you put 2 on all 4 sides. All right, so here is the periodic chart, and the blue regions, including helium over here, are the s orbitals, and the green have the p orbitals. So if they've only got 1 or 2 electrons in an s orbital, so the 1s, 2s, 3s, 4s, 5s, 6s, then it has 1 or 2 dots. And if it has more, then it's in one of the p orbitals. So these all have 3, these all have 4, these all have 5, these all have 6, these all have 7, and these all have 8. So all of the noble gases have their full valence. Now, helium is kind of an oddball because we know the first energy level does not have any p orbitals. It only has the 1s. So its full valence is just having the 1s orbital full. So that's why helium is put over here with the noble gases, because it's not very reactive, and it is not able, it's so small it's not able to have a p orbital. All right, and then the very, very end of this section gives kind of a conclusion again about talking about the progression of the atomic models that we've talked about. So we went from the Dalton model with the hard sphere to the Thomson plum pudding model to the Rutherford nuclear or planetary model to the Bohr energy level model, but with the concentric circles, to the Max Born electron cloud model, to the probability model that follows the Schrodinger equations. So that's the end of section 3.